Welcome back to Probability and Statistics 1. This is Unit 2 on choosing at random, and this is actually the second part of that lecture. In the first part, we talked about random selections of an individual from a population and simple random samples of a group from a population. In this part of the lecture, I'd like to address a different topic, that of sequential random samples. In a sequential random sample, the order in which individuals are selected does matter. This is directly in contrast to a simple random sample where order doesn't matter. And the reason is that in a simple random sample, we're picking subsets. And in a subset, the order in which elements are listed doesn't matter. Tom, Dick, and Harry is the same subset as Harry, Dick, and Tom. But in sequential random sampling, the order of selection does matter. And so we're going to represent outcomes as vectors rather than sets. So the vector Tom, Dick, Harry would not be the same as the vector Harry, Dick, and Tom because the order of the individuals listed is different. And so parentheses will denote vectors, and we'll continue to use braces to denote sets. Here's a question for discussion. The positions of president, secretary, and treasurer are to be filled in a club with 12 members. The positions will be filled by drawing names randomly from a hat. Assuming that all members are qualified for each job, how many selections of officers are possible if, first, no member can hold two positions simultaneously, and then secondly, any member can hold two or more positions simultaneously? So how many possible selections of officers are there in each of these cases? And the reason I pose these two cases is because that in sequential random sampling, we consider both sampling without replacement and sampling with replacement. Let's talk about sampling with replacement first. Again, we consider a set of capital N distinct objects that we'll call the population. A sequential random sample with replacement of little n objects from this population is a random process such that, first, each outcome is a vector of size n from the population, and then secondly, all vectors of size n from the population have the same probability. So if you think about this for a second, not only does the order of selection matter in a vector, but the order that elements are listed, but in a vector you can also have the same entry more than once, right? You can have a vector, for instance, of all ones. You can't have a subset of 3 copies of 1. That's just equivalent to a subset of consisting of the single element 1. There are no duplicates in a subset, but there can be duplicates in a vector. And this is the essence of the sampling with replacement. I could have the vector Harry, Harry, Tom, right? Where Harry got in twice and Tom just got in once. And that would correspond to the selection where maybe Harry is president and Harry is also treasurer, but Tom is secretary. So this is sampling with replacement. The idea of the terminology with replacement, you can think of drawing names out of a hat. If you're sampling with replacement, that means you draw a name out of the hat, it turns out to be Harry, say, and then before you make your second draw, you replace that name in the hat, so it's possible to draw Harry again. That's why we call it sampling with replacement. In contrast, a sequential random sample without replacement of little n objects from a set of size big N is a random process such that each outcome is again a vector of size little n from the population, but not just any vector. It's a vector in which no 2 entries are the same. And again, all these vectors have the same probability. So in a sequential random sample without replacement, outcomes are still vectors because order matters, but they're only vectors that don't have any repeats, that in which no 2 entries are the same. And that's, that's what you would get if you drew names from a hat, and once you draw a name, it doesn't get returned to the hat. So the next name you draw is definitely going to be different. So that's sampling without replacement. Again, in both these cases, the sample spaces are by definition equally likely. All these definitions said that all outcomes are equally likely. So we're going to need to know the number of possible outcomes when we sample sequentially with replacement and without replacement. And in sequential sampling with replacement, remember the outcomes were vectors of length n whose entries came from a population of size capital N. And our first bullet point here tells us the number of such vectors. It's capital N raised to the little n power. And this is essentially because you can think of building a vector like this as follows. You can say, well, select the first entry. You have capital N choices for that. Select the second entry. Because the sampling is with replacement, you still have capital N choices for the second entry. So you have n times n possibilities for the first two entries, n cubed possibilities for the first three entries, and so on until you get n to the little n power possibilities for all little n entries. So that would be the number of outcomes for sampling with replacement. For sampling without replacement, it's the permutations of capital N things taken little n at a time. Because think about building a vector for sequential sampling without replacement. You have n choices for the first entry, but then only n minus 1 for the second, n minus 2 for the third, and so on. And so you get this product of decreasing factors in which there are little n terms. That turns out to be just what we mean by big N, a permutation of big N things taken little n at a time. So this theorem gives us the number of outcomes in each of the cases, sampling sequentially and with replacement, and sampling sequentially and without replacement. Of course, then the probability models directly follow. Since they're equally likely, in sampling with replacement, the probability of any specific outcome is 1 over capital N to the little n power. And when sampling without replacement, the probability would be 1 over capital N P little n. And so in either of those cases, the sample spaces are equally likely, and so the probability of any event would just be, again, the cardinality of the event divided by the cardinality of the sample space. So a couple of different ways to think about those in either case. Another discussion question for you, and we'll again go deeper into these in class, but an urn contains 3 red balls and 5 white balls. Take a sequential random sample of size 4 from the urn. How many possible outcomes are there if the sampling is done with replacement? How many possible outcomes are there when the sampling is done without replacement? And what's the probability of drawing 2 red balls before drawing 2 white balls? Answer this both for sampling with replacement and sampling without replacement. So just let me expand a little bit on this. We've got 3 red balls and 5 white balls, but for answering parts 1 and 2, you want to think of the 3 red balls as still distinguishable. So you can think of, 8 balls may be labeled from 1 to 8. Balls 1 through 3 are painted red, and balls 4 through 8 are painted white. So think about it that way in answering questions 1 and 2 there. While in question 3, though, all that matters is really the color of the balls. And so there you're going to have to think a little more deeply in addition to thinking about, well, how would it be possible? What are the possibilities for drawing 2 reds before drawing 2 whites? Anyway, those are the questions to think about. And I'm going to end here with a little theorem that just kind of summarizes what we've seen in terms of just counting the outcomes in the various kinds of sampling spaces or sample spaces that we've seen for simple random samples and sequential random samples. So the number of ways to choose little n objects from big N distinct objects is capital N choose little n if the selection is done without replacement and order does not matter. That corresponds to simple random sampling. Big N P little n, the number of permutations of big N things taken in at a time, if the selection is done without replacement and order does matter. Capital N raised to the little n power if the selection is done with replacement and order does matter. And finally, this is actually a case we didn't consider, but I thought I would add it here to the theorem for completeness. It doesn't come up in random sampling so much, but it comes up in other contexts. How many outcomes would there be if you did the selection with replacement and order doesn't matter? Well, in that case, all you'd really need to do is specify the number of times you chose in each individual object. And it turns out that this binomial coefficient gives you the number of selections in this case. Again, this doesn't come up in random sampling, but it is something we'll see later. So that's it. Think about those discussion questions. We'll be talking about them in class, and some homework problems will also be related to them. And as always, if you have questions, please get in touch with me by email, and we will be back at you real soon.